today I'm going to be explaining how myelin sheaths actually help increase the speed, prevent degradation, and preserve energy of action potentials. And I couldn't understand this unless I truly got the physiology behind it. So I'm going to discuss some key concepts here. So first off, why are myelin sheaths important? So in an actual neuron, we have our myelin sheaths, right? And they're spaced out by these little nodes of ranvier, or however you want to pronounce it. But we have these nodes right here and the sheaths right here. And basically the combination of both of these things is what allows all of these three things to occur. So let's take an example of a cell that has a myelin sheath the entire way. I'm going to explain the importance of these nodes of ranvier. So electrotonic conduction is super fast, but it degrades. So if you look at this neuron right here, we have our input into the cell that triggers that positive influx of sodium. And what electrotonic conduction is essentially, if we have these positive influx of cells, naturally, positive forces are going to repel each other. So these positive ions that are within this other part of the neuron, they're going to repel each other, and this is going to continue down the length of the axon, but eventually it will degrade. If you just think about it, this one's going to repel, that one's going to repel. They're going to become more dispersed with time. So why? Well, what about this action potential, right? This threshold was reached. So let's say this became -30, but it's degrading to -40, -50. Well, why can't those voltage-gated sodium channels work? Well, with a myelin sheath, it covers those areas of these sodium channels right here. So if we had a cell completely covered in myelin, we would have degradation of the action potential and the voltage of the cell. So it would become more negative with time. And we don't have those sodium channels activated to put an influx into the cell. So electrotonic conduction is extremely fast. It's passive, but it degrades with time. So that's the point of the nodes of ranvier. Again, however you pronounce it. So this is our regular cell with nodes of ranvier and myelin. So I'm sure you can probably see how this helps already. So again, let's follow our stimulus, right? We have our sodium channel, our voltage-gated sodium channel providing an influx in. And a regular neuron conduction is this. So we have the electrotonic conduction slowly transmitting this positive signal throughout the cell. And eventually, right, it'll degrade. So I'm just using -30 as an example. It's probably going to be +30 in real life. But you get the point. So it's degrading. But now we have this opening. We have this opening where the sodium voltage-gated channels are active and can become activated because there's no myelin covering it. So then we're going to get that positive influx again, therefore increasing the voltage of the cell into a more positive number. So we're not losing that signal. It's going to continue. And that's why these signals kind of jump, right? They jump in between the nodes. And it's because we have this influx in at these areas because, yes, it's still triggered, but we need it because without this influx, it would degrade. So the conduction is faster because of electrotonic conduction. And I'm going to show you this here. If we just had no myelin, we had none of that, right? If we had no myelin, we could indeed conduct neuronal impulses. And so let's look at here, right? And I'm going to apply this to MS. So if we just had a axon that had no myelin and just these voltage-gated sodium channels, it would work. But again, it's this constant activation of doing these things. It's much slower, and it actually costs some energy. So it's going to be time-consuming, and it's not a passive, per se, process like the electrotonic conduction is. But it doesn't degrade. So someone with MS, where they have degradation of their myelin. That's why their neuronal impulses are much more slower. And we can see those with like dyskinesias and stuff like that too. But anyways, to put this all together right, we have our electrotonic conduction, which is fast, but it degrades. Then we have our regular sodium voltage gated channels, which helps with that positive influx in, and it will not degrade. So with the combination of our sodium channels constantly providing a positive influx in when threshold, which is negative 55 millivolts, is reached, in combination with the myelin, which helps promote electrotonic conduction, which is fast and passive, we have these extremely fast signals that jump, that save and preserve energy. It prevents degradation. That's the nodes of ranvier. It increases speed. That's the myelin, because it doesn't allow just sodium channels to be activated. It allows for that electrotonic conduction. And then it preserves energy, because we're not just using the sodium channels. We're only using them as needed. So that in a whole is how myelin helps increase the speed, prevent degradation, and preserve energy of a neuronal impulse.